It's a pleasure to introduce Sergei Pilugin from St. Petersburg State University. We're going to talk about shadowing properties of group actions.
Thank you very much.
First, I want to thank the organizers for inviting me, for creating this very interesting conference, and for the warm atmosphere around us. Maybe too warm in the street, but psychologically. Do I speak loudly enough? Do I need to? I will speak about shadowing properties of group actions. And first, I will recall some basic notions of the shadowing theory for the action of the simplest group or group of integers. I consider a metric space. Mostly, I will assume that it's a compact metric space, but also some results will be for Euclidean spaces or for n-dimensional complex spaces. So I consider a dynamical system generated by a homeomorphism pair. And the main notion of this theory is approximate trajectory, but now it is usually called D pseudo trajectory. So we fix the positive number D, and consider a sequence of points of my space and zero, Xn, and what we know, it is not necessarily mapped to the next point of the sequence, but if I apply my f and look at the distance between these 2 points, I know that it is less than this given. So we get an approximate trajectory, and as far as I know, pseudo trajectories appeared in a paper of Birkhoff on the three-body problem. So this name is usual for this conference. We've heard it many, many times, but here Birkhoff also was the first. And the main shadowing property, the main property which we now study related to such approximate trajectory is the, I call it just standard shadowing property, because now we have too many shadowing properties, and I'm also responsible for that. I introduced also some of them, and people introduce more and more, so I call it standard shadowing property, or it's called pseudo-orbit tracing property, coming mostly from Japan. So the shadowing property means that for any positive epsilon, there exists a positive D, such that for any such approximate trajectory, we can find an exact trajectory of some point x, such that these distances are less than epsilon. So for any approximate trajectory, there is an exact trajectory close to it. The first basic results on shadowing are due to Anosov and Bowen. And mostly people use hyperbolicity. It is not so difficult to show that if you have a hyperbolic mapping, then it has this shadowing property. Unfortunately, until now, we don't have necessary and sufficient conditions for shadowing, because it's not clear in which terms you can formulate such conditions. This theory is close, of course, to the theory of structural stability, but there is no hope that you can formulate conditions for shadowing in terms usual for structural stability, such as hyperbolicity and transversality, because it's very easy to show that the shadowing property is preserved under topological conjugacy, while hyperbolicity and transversality are not preserved. They are, how to say, C1 properties.
Isn't there also an issue about the type of failure of shadowing that you can have? You can be not shadowing in many ways, no?
Yes, yes, yes. Well, so now I will turn to group actions, the main topic. And here there was a problem because it's difficult to decide to what extent I have to define algebraic notions which I will use. So for me, psychologically, the answer is like that. If I remember something from my basic course of algebra at the university, I will not give a definition. If I don't remember properly, I will better give it. So I will
also authorized to ask definitions from you if you want to.
Yes. I will work only with finitely generated groups. So in a sense, this means that we pass to multidimensional time, but finite dimensional time, not dimensional. And left action 2, I will use multiplicative notation, and unit will be denoted by E, and the left action of a group G on a metric space, it's a mapping with this property for any element of the group. It gives me a homeomorphism. If I take a unit element, I get identity, and the group, natural group property, and the orbit of a point X under this action phi capital is this set. It will take all images for all elements of the group. So how to define a pseudo-trajectory? I take some generating set of the group G, S capital, a finite, since it's finitely generated, there exists a finite set. It is better to have it symmetric, so with any element it contains also the inverse element, and a set of points of my metric space with indices from the index by elements of G is called a D pseudo-trajectory of action phi with respect to generating set S if these inequalities are satisfied. So if I take the simplest non-trivial case, the integer lattice on the plane, it is natural to take as a generating set the actions which are given by these two and by these two elements of the group. And so what happens? We have this set. I take yj and I apply actions corresponding to elements of the generating set. And I compare, so if I take this and I take the next one corresponding to this element S of the generating set, then the distance to the exact, so this will be y as j, the distance is less than d. Of course, it's not an exact translation of this. To get an exact translation, I have to, in the case of a homeomorphism, I have to add an inequality of this type. But usually we work with good homeomorphisms F, at least such the inverse is uniformly continuous, so we get an equivalent notion. How do we define the shadowing property with action? I say that phi has shadowing property with respect to generating set S if for any positive epsilon there exists a positive d, such that for any d pseudo trajectory of that kind with respect to this generating set, there exists an exact trajectory satisfying these inequalities. So this is just exact parallel with this. So we have at any point any element of the group, we have this approximate trajectory value, and we have, say, by g x e. And the difference is less than. It's very easy to show this trivial thing, to show that if phi is uniformly continuous, so for some symmetric generating set, any homeomorphism of this form is uniformly continuous, then the definition does not depend on the choice of the generating set. It just will, you will have to take a different d for a given epsilon. So below I will not mention, mostly I will not mention generating set, just continuous that the action, just assuming that the action is uniformly continuous. So, how can we prove the existence of a shadowing property for a group action? We define the expansivity property of a group action. It's just parallel to the expansivity of a standard dynamical system. So there exists a positive constant such that if trajectories of 2 points are epsilon close at any element of the group, then the initial points are the same. This is just standard expansivity in this language. And it is said that the action phi is topologically anorthogonal if it has the shadowing property and is expansive. This is also a standard definition in the case of homeomorphisms, in the case of actions of the group of integers. And the main statement which I will discuss, we call it reductive shadowing theorem. It says if there exists one element of the group G, one element G small of the group G capital, such that this now is the standard dynamical system. If this standard dynamical system is topologically anorthogonal, then phi is topologically anorthogonal, and this means that it has the shadowing property, and it's also easy to show that the shadowing trajectory is unique if epsilon is less than this. So how? Yes, the first variant of this theorem was proved by me with my PhD student Amirov in 2003 for actions of Z to P. And I will say a couple of words how do you prove this. Let us also consider the lattice on the plane. So what do we assume? We assume that there is some element G such that this restriction action by degrees of G has the shadowing property. Then you take an arbitrary element of your group, consider this subgroup, and the restriction of the pseudo trajectory to this subgroup is a pseudo trajectory of this restrictive action. So you can find a shadowing trajectory for this set of points, and then you show using both shadowing and expansivity that if you take the same for any element under the action of an element of the generating set, then these shadowing trajectories are mapped by the corresponding action. If this was G, this was SG, then phi S maps the shadowing trajectory to the shadowing trajectory. And then you extend this to the whole group. Why we started with this simple case? Because we wanted to understand what happens with the linear actions of such a group on the complex space. In this case, if you consider a linear action, this just means that you select Zp, the dimension of the group, you select P pairwise commuting matrices, and the action is given by this simple formula, and it's more or less easy to give necessary and sufficient conditions of the shading property for this linear action in terms of the so-called Taylor spectrum. Taylor is a specialist in functional analysis who introduced the spectrum for families of pairwise commuting operators, and this family of P complex numbers belongs to the Taylor spectrum if there exists a non-zero vector P such that this inequality is closed. So V is an eigenvector for any matrix ADA with its own eigenvalue. And the necessary and sufficient conditions for the shading property in this case is that for any element of the Taylor spectrum, there exists at least one component with absolute value different from one. Yes?
Did I give the definition of the Taylor spectrum?
Sorry?
Did you give the definition?
Yes. Here's the definition. So this is set of p-dimensional complex vectors, lambda, with this property. For this vector, there exists a unique non-zero vector V, such that this V is an eigenvector and of course later it was understood that the main property which is used for in this proof of the reductive shadowing theorem is the commutativity of the acting group. I will call it abelian, a commutative group. But now I have to go deeper in algebra to define what is called a virtually nilpotent group.
In the previous theorem, if there is no Taylor spectrum, then you have the shadow property.
How do I? No.
The one
you have shadowing property if and only if in any element of the Taylor spectrum there is at least one component with absolute value different from.
So if it's empty, it's
No, it's, in this case it's non-empty, it's standard, it's easy to show. And also it's easy to understand that if P equal 1, then the Taylor spectrum, we have only one matrix. We have just a linear action.
because they commute.
No. If P equal 1, we have only one matrix. It commutes with it.
We did set.
Yes, and then its Taylor spectrum is just the usual spectrum.
Okay, no.
This condition means that you don't have eigenvalues with absolute value equal to 1. So, yes. Now some algebra. I recall that the subgroup H of G is called normal if this equality holds for any element G. I define the commutator, and for two groups the commutator generated by commutators of elements. And now the definition is inductive. A commutative group, an abelian group, is nilpotent of class 1. And after that, we say that the group is nilpotent of class M. If there exists, this is called lower series, if there exist subgroups with this property, so any next one is the commutator of the previous with the group G itself, and it ends at the unit element.
Shouldn't GI be the commutator of GI with GI?
Sorry?
The last thing you wrote there, GI plus 1, is it the commutator with of GI with G or GI with GI?
With G. With G.
Ah, yes.
Yeah, that would be the old.
So, and a group is called virtually nilpotent if it has a normal nilpotent subgroup of finite index that the factor group is found. I'm sorry, maybe it's too heavy algebra for the first glance, but why are they important? There is a famous result by Michael Gromov that any group of polynomial growth is virtually nilpotent. Now, it was a surprise for me that Gromov also got a kind of a theorem which is a kind of reductive shadowing theorem. He published a long paper in a volume devoted to 80 years of Stephen's Mail, superstable pattern horseshoe. But he, in fact, there is no theorem of that kind inside the text. It's just a lemma in the proof of some theorem of C1 stability, but I selected it as a separate theorem. So it's easier for him, and that's what he needed to work with Lie groups. So H is a simply connected nilpotent Lie group. And there is a hyperbolic automorphism, sigma. For a Lie group, it's a standard definition. So if you consider the automorphism of the Lie algebra corresponding to sigma, in our language, you take the differential of the tangent space. And it is hyperbolic. Then every group sigma capital, subgroup of H which contains this sigma, if you assume that all its elements commute with sigma, then sigma capital has the shadowing property. The difference between the reductive shadowing theorem and this Gromov's result is like that. In the reductive shadowing theorem, you have a group. You select a one-dimensional subgroup, and you say that in this case, the group itself will have shadowing property. Here, he selects this one-dimensional subgroup generated by sigma small, and describes for which subgroup sigma capital you have the shadowing. The hyperbolicity implies the shadowing property. In a sense, the inverse statement. Just recently, but I know that they did not know this Gromov result when they wrote this paper, it was published later, that the reductive shadowing theorem is valid for virtually nilpotent groups. So, not only for integer lattices, but all groups with polynomial growth. But, as I say to my students, when you do something with algebraics, be afraid of algebra, because algebra is too complicated for us people from the I will show you. In algebra, there is a very well source of counter-examples. They are called bound-slug solitary groups. These are groups with two generators and one relation. If n equals 1, of course, you get an abelian group. But if n is more than 1, you get, in a sense, a very complicated group. And in the same paper, Osipov and Tikhomirov studied linear actions of the bound-slug solitary group on the plane. And the result for me was quite unexpected. You don't have an analog of this reductive shadowing theorem. What happens? Of course, you have one element. Lambda is a real number more than 1. You have one hyperbolic element. So the action of this, of the corresponding subgroup, has the shadowing property, it is expensive, everything is very good. But now the reductive shadowing theorem holds under a relation between this lambda and this n in the I call it the exponent of the bound-slug solitary. So if lambda is between 1 and n, this acts hyperbolically, everything is very well, but nevertheless we don't have the shadowing property. And if lambda is large enough, then you have. So this is algebra. And the proof really, in some senses, really algebraic. They have to prove a lot of relations to this. And if the group is very large, for example, if you take three groups with at least two generators, then no linear action will have the shadowing property. So for large groups, everything is bad. Now I turn to a different shadowing property related to this. So what happens here? We start with an approximate trajectory, and we are looking for an exact trajectory close to it. If we have in mind numerical methods, the shadowing property means you take a computer, you get an approximate trajectory, and if your system has the shadowing property, you can be sure that there is a real trajectory near it. But you can reverse the question. Assume that I have a numerical method. Assume that I have a real trajectory. Does this numerical method produce a trajectory which is close to the chosen exact one? It's also a natural question. And the corresponding property was called inverse shadowing property. But if you look at the problem like that, for any exact trajectory you have to find an approximate trajectory near it. You have you need a source of approximate trajectories. You need many approximate trajectories because you have many real.
Does it relate to specification in some way?
Sorry?
Does it have anything to do with specification? Specification?
No.
No. But
So, what is one of the possible formulations? I take a dynamical system generated by a homomorphism F, and I take a family of continuous mappings of my space M to itself, and I say that this family is a D method if these inequalities hold. So, you take point X, you apply gamma n, you apply gamma n plus 1, and your exact mapping must take this point to its f gamma n x, and this distance is less than. I call a sequence the trajectory of these D methods if these equalities hold, and it's easy to understand. It's clear that the trajectory of a D method is a D to the trajectory. And now the inverse shadowing property of F means that for any positive epsilon, there exists such a positive D. There exists a positive D such that for any point X from M, and for any D method gamma, so D depends on epsilon. There exists a trajectory psi produced by this method such that these inequalities hold. This precisely means that you take an exact trajectory, you take a method producing approximate trajectories, and it must produce a trajectory. There is a natural analogy of this notion for group actions. You consider an action, you consider a finite symmetric generating set, and a D method for my action with respect to this generating set is a family of continuous mappings of my space M indexed by elements of the group G, such that these inequalities hold. But this is precisely an analogy of what was here. Here I took S equal to 1. So gamma SG is analog of this, and F T capital of S is an analog. Here, application of F is just, it corresponds to using this element of the generating set. And the problem was how to prove analogs of reduction theorem, and the main difficulty was like that. you can define expansivity property for your system. Two trajectories which are close must coincide. But this is, an analog of this is impossible when you pass just to continuous matrix. Well, I'm sorry, I had to define an analog. So inverse shadowing for a group action is defined precisely in the same way as inverse shadowing for action of for a dynamical system generated by homeomorphism. For any positive epsilon, there exists a positive d, such that if I take any exact trajectory of a point x, and I take any d method in this sense, then it produces pseudo trajectory such that they are epsilon. And here I had to introduce something which doesn't have analogs. Maybe in a sense it has an analog. It is an analog of expansivity property. So let me take an action of a group G. Fine. Let me take a D method. Let me take a point of my metric space at a positive number epsilon. And a tube with this notation is a family of trajectories, approximate trajectories generated by this approximate method, numerical method, such that they are close to the exact trajectory in this sense. It is important that we have a non-strict inequality here. And I defined what I call the tube condition. Again, I consider action of a group G. And tube condition, there exists a constant A, such that for any positive epsilon, there exists a constant D depending on epsilon, such that if gamma is a D method, then the tube of size epsilon is not empty, but any tube of size A of this size coincides with this epsilon tube. So you take, of course, the picture will be for homeomorphisms. You take an exact trajectory and there is a positive A such that for any positive epsilon I can find a constant D independent of epsilon such that I have approximate trajectories which are epsilon close to Z1, but I don't have more. I don't have approximate trajectories at distance A, which are not approximate trajectories at distance epsilon. And in the, of course, on the best understood case, I mean hyperbolic linear automorphisms, the tube condition is satisfied. This is corollary of standard estimates, but even for a hyperbolic linear automorphism, it's possible to have uncountably many epsilon closed trajectories, different. Not one, as in the case of if you would like to give an analog of expansivity, we would expect to have only one approximate trajectory. No. The simplest situation I consider this linear expansion on the line, and I construct I fix small positive delta, and maybe I'll give the picture. So this, I take P equal to 1, so I consider the trajectory of P equal to 1 in this system, and the mapping gamma k for positive k looks like that. 1 plus delta 2 8. So here and here it is the original mapping, and here I have this step, and it is easy to see that if I take epsilon not less than p, then this epsilon 2 consists of all sequences zk such that they coincide for non-positive k. They are 2 to k z0, where z0 is from this interval, and 2 to k for non-negative k. And so there is an uncountable family, because z0 takes k. And the reductive inverse shading theorem, which I published recently, shows that for, okay, let phi be a uniformly continuous action of a finitely general virtually nilpotent group, and if there exists an element G small in the group G such that this restriction of the action to the one-dimensional subgroup generated by G satisfies the tube condition, then phi has the inverse shading. So in a sense, of course, some induction along this definition of a virtually nilpotent group is used to show that the tube condition for a subgroup implies the tube condition for the previous subgroup. So you, in a sense, you lift this tube condition along the definition of a nilpotent group, because virtually nilpotent group is just also the same, because it is a finite factor. Well, and how many times? the last word. My PhD student Fajr just now showed that this theorem is not valid for Baum's solitary group, and a very simple example of the action of that type on the line. Thank you.
Question?
Yes.
It reminded me of a question which is related to your talk, which is the closing lemma for group actions. You take a group action and you look for a finite pseudo-object. Even in the C0 case, it's an open question.
What's the question?
I'm ashamed, but I never thought about closing lemma for multidimensional time.
You should take the classical closing lemma for one homomorphism.
Yeah, I know.
It's completely trivial in the C0 category.
Yes, of course it's
If you take
still.
a group action, you can look for a finite set, which is a pseudo-orbit, and this is the exact analogous to the closing lemma. Even in the C0 case, it's a wonderful question.
Thank you. Thank you. It's very interesting.
For all type of groups, which are not dense,
For abelian groups, I think it's possible, but for non-abelian groups,
so you can
I
compress and
know
divide and
some
compress.
examples where there is no approximation. For example, if the group is simple, it cannot have a finite orbit because it does not have a subgroup of finite index. But I think this question is maybe
It's a very good question.
maybe
Thank you.
easy and interesting.
Thank you very much. Very good question. Yes?
There is, as you mentioned in the case of free groups, there are examples where it doesn't hold, or
For free groups with two elements, you see, it has too many elements in a sense. It grows exponentially. So, I mean the number of words of six length grows too fast, and this creates.
that the objection is the number of elements that you create, not the dynamic.
Not precisely, but in a sense, yes.
It's the group structure, not the kind of dynamics that you have in the omniums.
The group structure, but here also the group structure is what is bad.